All right, guys, next lesson on circles is 10-7 special segments in a circle. In our last lesson, we focused on what happens when secants and tangents intersect inside and outside the circle and what angles they form. And now we're going to focus on what happens when secants and tangents intersect either inside or outside the circle and how to find the lengths of the segments that creates. So that's what we're going to work on here. We're going to need some new vocabulary. We're going to talk about chord segment. And these are segments created by intersecting chords inside a circle. So if we end up with two chords crossing inside the circle, then we end up with these individual segments. Perhaps we could call this A, B, C. We end up, this chord has two segments, A, B, and B, C. Secant segment, likewise. A secant segment is a segment of a secant that has exactly one of its endpoints on the circle. And so for that reason, we would call perhaps not this piece, not a secant segment, because that's a chord, right? It's got both its endpoints on the circle. But if we had perhaps point D here, and maybe this was point E, we would call DE a secant segment because only one of its endpoints is on the circle. And then we could say, if we were to call this point F, then we could have an external secant segment. And so DF would be an external secant segment because it has just one of its points on the circle and it lies outside the circle, or it's on the exterior. And also we are going to talk about tangent segments. A segment of a tangent with one endpoint on the circle. So we've talked about tangents, and a tangent just touches at one point. So if we're talking about a tangent segment, of course a tangent here, if we called the L, it goes on forever in both directions. But what if we called this point G and this point H? Well, GH here would be what we call a tangent segment. All right. Let's see what we can do. Let's work with these and see where they take us. All right, our first theorem of this lesson, circle theorem 15. If two chords intersect inside a circle, then the products of the lengths of the chord segments will be equal. In other words, we have these two chords, RT and SU, that intersect inside the circle. And when this happens, RV times VT will equal UV times VS. I also gave these segments, these lengths A, B, C, and D. So you could say A times B equals C times D. Now, I'm not going to prove it right now, but I am going to do a video that I'm going to attach to this lesson that proves all the theorems in this lesson. Just give you a hint, where could this possibly come from? A times B equals C times D. Those look suspiciously like cross products. And where do cross products come from? They come from proportions. And where do we use proportions in geometry? When we have similar triangles. Could there be similar triangles hiding in this diagram that we could use to prove this circle theorem 15? Tune in for the next video and I will do that proof. In the meantime, let's go on and do some examples. All right, based on our circle theorem 15, here could we find X? We've got two chords, RT and SU, that intersect inside the circle. And so the product of their segments should be equal. So 27 times 3, this segment times this segment, 27 times 3 should equal this segment times this segment, 9 times X. Okay, 27 times 3, that gives us 81. Equals 9x. We can divide both sides by 9 and we get 9 equals x. Okay, so that's a good application of circle theorem 15. The product of these segments is always going to be equal. That segment times that segment always equals that segment times that segment. All right, let's try a slightly trickier one. Same idea here. They want us to find x, and circle theorem 15 is going to work for us here. We know the products of the segments, the chord segments, are going to be equal. So why don't we write those out here? X times x plus 5. That should equal this segment times this segment. X plus 1 times x plus 3. Okay. Can we clean all this up and solve for x? And when we distribute x here, we get x times x is x squared, plus x times 5 is 5x. And here, when we FOIL this, x times x is x squared, plus x times 3 is 3x, plus 1x, plus 3. And we can combine some like terms over here. If you want, you can go ahead straight away. I know those of you who like to solve quadratics are going to be disappointed that the x squareds are going to drop out. You subtract x squared from both sides, they go away. Yeah, so maybe next time we'll get to solve a quadratic. It won't be so disappointing. 3x plus 1x is 4x plus 3. And we can subtract 4x from both sides. And I find that x equals 3. Good. All right, great time to pause the video if you want to try this on your own. It's very similar to the last problem. They want us to find x. We know the products of the segments, this times this, should equal that times that. Let's go ahead and see if we can solve that for x. X times x plus 11. Okay, that segment times that segment should equal this segment times this segment. X plus 5 times x plus 3. Good. And when we distribute here, we get x times x is x squared, plus x times 11 is 11x. Here we're going to FOIL, and we get x times x is x squared, x times 3 is 3x, plus 5 times x is 5x, plus 5 times 3 is 15. Okay, and this time, may not always happen, but this time the x squareds cancel out, don't they? We can subtract x squared from both sides. Get 11x equals 3x plus 5x gives me 8x plus 15. I can subtract 8x from both sides. And I get 3x equals 15. We can divide both sides by 3. And we get x equals 5. Good. All right, what has Dave got going on now? Dave has a 15 millimeter diameter axle that he wants to modify to a D shaft profile by cutting it along RT. If the depth of his cut SV is 3 millimeters, how long is segment RT? So this is a cross section of an axle, or think of it like maybe a dowel, that he wants to cut. It's got a 15 millimeter diameter, and he wants to cut it like this so it's got a flat face that he can use as a D shaft. Okay. All right, so if it's 15 millimeter diameter, that tells me that SU is 15 millimeters, right? And he wants to cut it so that the depth of cut SV here is 3 millimeters. Okay. Well, if that's 3 millimeters, then this segment VU would be 15 minus 3 would be 12 millimeters. Good. And they want to know how long is segment RT. Okay, so if he was calculating the depth of cut, he was talking about the distance from this point S to this line RT. And distance from a point to a line, that is a perpendicular distance, isn't it? Okay, so that tells us we've got a right angle there. That's significant. What did we learn earlier in this unit about what happens when a chord intersects a diameter or a radius at a right angle? That radius or diameter ends up bisecting that chord, doesn't it? Ends up, if you wanted to, you could draw from the center here, these two radii, and all radii in a circle are congruent. And so you can see that this really is an isosceles triangle. And that means that we're dealing with a perpendicular bisector. And so this base gets cut into congruent segments. All right, how long is RT then? How does that help us find RT? Well, could we call this segment X? Would that make this segment X? And does RT equal 2X? We could do that, right? So now this looks like our other problems. This is not too bad. 3 times 12, the product of the segments, 3 times 12, should equal the product of the other segments, X times X. So we get 36 equals X squared. And how am I going to solve that for X? Swish and flick. Take the square root of both sides. You get 6 equals X. Of course, next year in algebra 2, you will find that X equals plus or minus 6. but in geometry, we keep the positive root, only positive distances make sense for us. So how long is RT? It's 2x, 2 times 6. 12. What are our units? Millimeters. Good. Good job, Dave. Okay, now Dave is installing an eyebrow window in an office building. If the window is 10 feet wide, what is the radius of the curved portion of the window? Okay, and they're telling us that this is 2 feet, this maximum distance. The technical term for this is the mid-ordinate, if you wanted to call it that, from here to this straight chord. Okay, so how are we going to be able to figure out this radius? Like, where is even the circle, right? Well, your circle, you can picture it continuing on, and it has some radius, right? So there's, wherever the center is, it's got some radius to it. Okay, so how could we figure this out? One thing we do know is we have this chord that cuts across here that is 10 feet long. And then we have this segment. If we drew it from the peak, that'd go down through the center here until we hit the center of the circle, whatever it might be, right? And so this would be R, and this is 2. So this piece right here, isn't this R minus 2? Could we do it like that? Right? From the center to that point would be the radius. And so this chord segment is 2 feet. And then this is R minus 2. The problem is getting to the center of the circle doesn't get me another chord segment. All right? That gets me a part of a radius. So maybe what we should do is we should have this go on to the diameter, right? So we could say this is the diameter minus 2, right? That might be easier to work with. Okay. All right, so now I've got 2 segments, and we know that when we draw this, that these are going to get bisected, right? So each of these is 5. And if you want to break this out now at this point, you can say, hold on, I'm going to draw my circle. I want to see the whole circle while I'm doing this. And you can say, there's my circle. That guy is 2. This guy's 5. That guy's 5. And this guy here is D minus 2. Okay. Just turn it into a problem that you know how to solve. So we know the product of these segments is going to be, they're going to be equal. So 5 times 5 is 25, is going to equal 2 times D minus 2. We'll solve this for the diameter, and then we'll cut it in half so that we can find the radius that they were asking for. 5 times 5 is 25, equals 2D minus 4. Good. I can add 4 to both sides, and I'm going to get 29 equals 2D. And if I divide both sides by 2, I'm going to get 14.5. My units are feet, equals the diameter. Okay, if that's the diameter, what's the radius? The radius equals 1/2 the diameter. It's going to be 1/2 times 14.5. Our radius equals 7.25 feet. Good. All right. Good work, Dave. Okay, that brings us to circle theorem 16. And this one tells us if 2 secants intersect on the exterior of a circle, you can see VS and VT are secants, then the product of the measure of one secant segment and its external secant segment is equal to the product of the other secant segment and its external secant segment. Okay, what the heck does that mean? What it's saying is that the product of one secant segment, VS, and its external segment, VR, will always equal the product of the other secant segment, VT, and its external segment, VU. So VS times VR will always equal VT times VU. This is very important to remember that it's slightly different than when chords intersect inside the circle. You just multiply the two segments. But here you got to be careful. It isn't A times B equals C times D this time. No, 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 no. It's A times A plus B equals C times C plus D. Okay? And we can prove this. I'm not going to go ahead and prove it now, but in the next video, I'm going to do a full proof of this. Very interesting proof. And again, I'll give you a little hint if you want to start to think about the proof yourself. VR times VS equals VU times VT. Those look suspiciously like cross products to me. And I'm suspecting they come out of a proportion. And in geometry, when we do proportions, we're talking about similar triangles. Yep, believe it or not, there's similar triangles hiding in here that'll help us prove this theorem. In the meantime, why don't we go ahead and try to apply this? We know that this secant times its external segment equals this secant times its external segment. Let's try some problems. Oh my goodness, what's that? Cool. All right, here could we find x? You can see we've got two secants intersecting at point V on the exterior of the circle. And one of the secant segments is VS, and its external segment is VR, and the other secant segment is VT, and its external segment is VU. Okay, so I should be able to say 6 times, how long is this secant segment? You might want to get in the habit of doing this so that you don't accidentally multiply 6 times x. The whole secant is x plus 6, isn't it? So 6 times 6 plus x, or x plus 6, should equal this external segment, 10 times, how long is VT? If that's 10 and that's 20, then VT is 30 units long. So 6 times x plus 6 should equal 10 times 30. That's how you set it up. Can we solve that for x? Absolutely. Let's distribute the 6. We get 6x plus 6 times 6 is 36 equals 10 times 30 is 300. I'm going to go ahead and subtract 36 from both sides. I get 6x equals 264. And if I divide both sides by 6, something tells me I'm going to get 44. Is that right? Never trust your math teacher. 264 divided by 6. Hey, look at that. Perhaps you want to pause the video here and try this one on your own. This one is slightly different, but same idea. We've got two secants intersecting in the exterior of the circle at point A. So could we figure out x based on that? Well, I've got this external segment 25 and this whole secant AC. I'm going to do this. 25 plus 27 is 52. Okay, so I know that 25 times 52 should equal the other external segment, x, times, excuse me, how long is AE? It's x plus 24, right? Oh, this is going to be exciting because you can see when the variable's in the external segment, we're going to end up with a quadratic. That'll be exciting. All right, 25 times 52. Something tells me that's 1300. I don't know, you might want to check me on that. X times x gives me x squared plus 24x. Okay. All right, how are we going to solve that? Let's see. Did we in fact 25 times 52? Yep. Remember how to solve quadratics? We've got to factor them. And to do that, we first want to set them to 0 so that we can use the zero product property, right? So we get 0 equals x squared plus 24x minus 1300. Okay, all right, I need two numbers that multiply to negative 1300 and add to 24x. I'm going to continue my work down here. And I like to set these up as a 6-piece puzzle. Hopefully you guys remember showing remember me showing you this 6-piece puzzle, 1, 2, 3, 4, 5, 6. In order to have gotten x squared, you know, when a equals 1 out here, it's nice because in order to have gotten x squared, I must have multiplied x times x at one point. In order to multiply to a negative number, I must have opposite signs. I must have a positive and a negative. I got 4 pieces of my 6-piece puzzle. Cool. Now I need 2 numbers that multiply to 1300 and add or subtract to give me 24. How are we going to do that? I think we're going to have to factor that 1300 until we get what we're looking for. We already have these 2 factors of 1300. The problem is the difference between them is 27, not 24. So let's go ahead and factor 1300. We're going to list our factors of 1300 and see if they add to positive 24. Okay. Factors of 1300. Well, if you want, start with 1300, and since we might as well bring the signs along with us. 1300 times negative 1. Well, that's going to give me 1299. Doesn't work. And here's a little thing that I like to do. Just split that in half and double that one and just keep going. 650 and negative 2, right? Well, that'd be 648. Okay, split that guy in half and double this one. That's not quite going to do it, but maybe we're converging on a solution here. So 325 and negative 4 gives me 321. We're getting closer, but I can no longer split this guy in half and end up with a whole number, right? So, but I could think about dividing 1300 by 5, right? So 1300 by 5, what do we get? We get 260. So I could say 260 times negative 5. That gives me 255. Not the 24 I'm looking for. Let's keep trying. I'm going to cut this in half and double that guy. 130 times negative 10. I end up with 120. Okay, let's keep going. Cut this guy in half, 65, and negative 20. I end up with 45. Oops, and I can no longer divide that guy in 2. Okay, I could try to jump in and say it is 13 times 100, right? So we could say 100 times negative 13. Good. That would give us 87. All right, let's cut that in half and double that one. Now I'm at 50 and negative 26. Oh, look at that. Those add up to positive 24. Good. Hey, we found our factors with our little factoring table. All right, so I'm going to end up with x plus 50 times x minus 26. And the reason we do this is our zero product property, right? If I told you 0 equals j times k, what can you tell me about j and k? At least one of them must be 0 to make this equation true. And when we split a quadratic into 2 binomial factors, this times this, we know at least one of them must be 0 to make this equation true. So we can solve 2 conditions now. X plus 50 equals 0 and x minus 26 equals 0. Okay, both of these will be solutions that work for this equation. So obviously this one, you can see where it's going. Doesn't work for us in geometry. Next year in Algebra 2, you have to keep that root. Not going to keep it today. Here we add 26 to both sides, and we get x equals 26. In geometry, we're looking for positive distances. This makes sense to us. Good. All right, next theorem, circle theorem 17. Now we're going to take and we're going to intersect. Instead of 2 secants outside the circle, we're going to take and intersect a secant with a tangent segment. Okay, so if a tangent and a secant intersect in the exterior of a circle, then the square of the measure of the tangent is equal to the product of the measures of the secant and its external secant segment. What the heck does that mean? Okay, all it means is the tangent times the tangent. Now remember, there was a little bit of duplication in that last theorem. We multiplied a secant's external segment by its whole length. And essentially that's what we're doing here too, except this tangent has gotten to the point where instead of being a secant, boom, at the point where it just touches the circle, now we call it a tangent. But guess what? the same idea applies. And it'll make more sense when I prove this theorem in the next video. And yes, as you might suspect, RU squared is RU times RU equals RS times RT. These are, again, cross products, and they come from proportions which come from similar triangles. When you see that proof, this will make more sense. But for now, we can just go ahead and recognize that RT times RS, this secant times its external segment, is going to equal this tangent times itself. Think of this tangent as having its external segment equal to itself. You could think of it that way, and that makes it a little easier in my mind. That's how I remember it. So in other words, A times A plus B will equal C times C, or C squared will equal A times A plus B. Let's try a couple of examples. Okay, here they want us to find x. This is that condition where a secant intersects a tangent on the exterior of a circle at point R. So I know that I'm going to take my tangent and I'm going to multiply. It's going to be x times x, or x squared. That's going to equal the secant's external segment, 25, times what is the total length of the secant segment, RT. This guy here is 45. So x squared should equal 25 times 45. Okay. All right, so I think we're going to get x squared equals 25 times 40 is 1,000. And then 25 times 5 is 125. So this is 1,125. Does that sound right? So to solve for x here, this one's not so bad because we have no bx term. These are easier to solve. We can simply take the square root of both sides. And we get x equals square root of 1,125. We get 33.5. Is that right? 25 times 45. 1125, yep, square root. So we get x equals approximately 33.54. That's what we'll call it. Good. All right, let's try one more of those. Condition where we've got a secant intersecting a tangent segment outside the circle. Here we know the tangent segment times itself, 12 times 12, or 12 squared, is going to equal the secant's external segment x times, if this is x and this is x plus 2, what is the total length of RT? Make sure you get this right before you set up your equation. X plus 2 is 2x plus 2, isn't it? So we're going to multiply our external segment times the total secant segment, which is 2x plus 2. Good. All right, this is looking exciting. 12 squared, that's gross, equals x times 2x is 2x squared, plus x times 2 is 2x. Good. Okay, again, we've got a quadratic here with a bx term, so we've got to use that factoring technique to solve it. We're going to subtract 144 from both sides. I don't know if you guys have a copy of Mr. Rogers' handy-dandy factoring flowchart, but the very first thing you hit in my flowchart when you're factoring quadratics is, do you have a, what's a GCF? Greatest common factor. Because remember, when A is 1, these are super nice to work with. Turns out we do have something we could factor out of all of these, right? We could divide all of these by 2. So we get 0 equals, or we could factor out a 2, and we'd be left with x squared plus x minus 72. Good. All right. We don't really need to worry about this 2 guy, but let's go ahead and set up our 6-piece puzzle just like this. We're going to have x something something, x something something. Okay, since I'm multiplying these last two numbers together to get a negative number, and I'm going to have opposite signs, and already I have 4 pieces of my puzzle. Okay, so what numbers multiply to negative 72 and add to positive 1? You got 9 times 8 is 72, if I had positive 9 and negative 8, they would add to positive 1. That's what I'm looking for. X plus 9 times x minus 8. Good. All right. So if this times this times this equals 0, what can you tell me about these factors? At least one of them must be 0, and it's not that one, so I'm not worried about him. X plus 9 equals 0. That's a possibility. And x minus 8 equals 0. That's my other possibility. You can see this one's going to get you a negative number, so we're done with him in geometry. Here we'll add 8 to both sides, and we get x equals 8. Okay, good. All right, that is my lesson on special segments and a circle. Don't forget to watch my next video where I prove those 3 theorems. I'm telling you, it's going to help hugely. It'll be really big for helping you remember those theorems, being able to prove them, and being able to rederive them if you forget them and you need them in the future. All right, good luck on the homework, guys. Don't forget to watch the proof video. Thanks for watching.